Okay, so compound interest. You guys can hear me, right? Somebody say confirm. Sometimes I do things and then all of a sudden there's no audio.
Yeah,
Good.
yes.
Thank you. Okay, cool. So, all right, compound interest. So I'm gonna try and develop the formula for it. That's the goal here. So what I'm about to do is overly complicated. Don't worry, this is not what you're expected to do on a regular basis. I'm going to use this example to develop the formula we need, and once we develop that formula, it's a pretty easy formula to use. So let's say that we have a case where we want to invest money, and it's like a real simple situation where we begin with our starting balance. Oops. Starting balance is over here, and I think I did 5,000 last time, so let's just stick to it. So some of this will be review, like I said. So let's say I started out with $5,000 to invest, and after a set period of time, and the period of time is usually 1 year. It's the most common kind of thing, and that's because interest rates are usually given in terms of a year. So let's say that the investment is paying off at a rate of interest rate is 5% annual. And that so it's annual interest rate, and so we'll have time over here. All right, so interest rate, interest earned is going to be the next column here. Interest earned. So we're going to go in, since this is given in terms of a year, we're going to go in annual intervals. So interest earned after 1 year. In 1 year. Okay, so here we're going to go with year number. I'm not happy. Okay, so year number 1. And I'm going to put that in color since I want that to kind of pop out after 1 year. Okay, so, well, anyway, okay, so interest earned. So interest earned is just going to be the 5% that you get on the 5,000. Good. So it's just going to be a formula of 0.05 times 5,000. Good. So 10% is 500. Half of that is 250. So you're going to make $250 the first time. All right, so at the end of the year, you're going to have your original balance plus the interest you just earned. However, instead of, so it's going to be $5,250, right? However, let's say I want to write it this way. So I want to write it as the 5,000, say end balance, end of year balance. So it's going to be the 5,000 plus the $250. So I know it's going to be 5,250. But instead of writing it this way, I want to write it in the following way. This $250 came as a result of multiplying these two things together. So I'm going to replace it with 5,000 times 5,000 times 0.05. Right? That's what this is. Plus 5,000. 5,000 plus, and then a multiplication of these two numbers. That gives me that interest earned. And now what I want to do is I want to factor out the 5,000. Put it out here. 5,000 times 1 plus 0.05. Okay, so then if I add these two things together, it gives me 5,000 times 1.05. Okay. So then if we multiply those together, if we get a calculator and multiply these together, you'll see that you get the exact same number, 5,250. So 5,000 times 1.05 is 5,250. Good? Okay. It sort of makes sense if you think of it in terms of percentage, right? Note that 1.05, when we converted it into a percentage notation, right, we moved 2 decimal places, that's 105%. Yeah, you started off with 100% of your money, you got 5% annual interest, so at the end of 1 year, you get 105% of your money, right? So you can think of it that way. Good, okay, so then we're off to year 2. The initial balance at the beginning of year 2 is now $5,250. $5,250. But as we just said, another way of saying $5,250 is to say 5,000 times 1.05. Okay, we'll keep that in mind for a second, but anyway, it's this amount. So at the end of this new year, you're going to also earn interest. And the fact that you're going to earn interest not just on your initial investment, but now you're going to earn interest on the interest you earned at the end of the first year, right? That's the part that's called compound interest. The fact that the money you made in interest from the first year is also going to earn interest on its own. The money you make makes money. Money makes money. It takes money to make money, right? That's how rich people stay rich, man. They have a bunch of money and then their money makes money, so they just gotta kick back and watch their money grow. All right, so let's multiply these two things together. And what do we get? 0.05 times 5,250. That's going to be $262.50. And notice, of course, that you're making a little bit more money. The previous year, you only made $250, but this year you're making $262.50, right? An extra $12.50. That doesn't seem like much, no big deal. But what if these were in terms of millions, right? You have $5 billion, which means that you earned $250 million in interest, just leaving it alone, not doing anything. And then your earned interest, so the following year you made an additional $12 million, right? For nothing special, you're just getting richer, an extra $12 million the following year. And the following year after that, you're going to make even more money, right? You're slowly making more and more and more and more without really doing anything, right? You're just letting your interests work for you. Okay, all right, so moving on then. So now at the end of your second year, you're going to have your initial balance, which was this $5,250, plus your new interest, which is $262.50. So we can just add those two things together, and of course you're going to have $5,512.50. Good? Okay, so that should be the balance at the end. Oops. Wait, what did I do? This is wrong. This is 5,200. Why did I put 55,000? 10,512. $10,512.50. $0.50. Okay, so that's a perfectly good balance. But again, we're going to try and see a pattern. And to do that, I'm going to make some replacements. We said from before that another way of saying 5,250 is to say that it's this little multiplication, right? This multiplication is that initial balance, right? We got that from the line right above. So I'm going to replace this 5,250 with 5,000 times 1.05, okay, plus, and now this 5,262 was the multiplication of these two numbers, so that one should be 5,250 times 0.05. That's what gives me this number here. Right? And what we just said that 5,250 is the same as this one, so I'm going to repeat it one more time and say that this is 5,000 times 1.05. And like I said, this is getting really tedious. Remember that this is just so we can develop our formula, and then once we develop our formula, we never have to do this again. So you're not going to be expected to be repeating this on your own. I just want you to understand where that formula comes from. Okay, so this I just copied down. Here, the 5,250, I replaced it with 5,000 times 1.05. And then once again, we can see that we can factor these two. This is identical to this, so we can factor it out. Put it out here on the outside of the parenthesis, 5,000 times 1.05. And then on the inside, we have this plus this, right? Blank plus blank is going to be on the inside once we factor that out. Factoring out 5,000 times 1.05, we end up with a 1 here. And then for the second term, the only thing that remains is 0.05, right? Which can be combined again, and we end up with 5,000 times 1.05 times 1.05. And they're identical, so of course we can rewrite them as 5,000 times 1.05 to the power of 2. Okay, so at the end of the second year term, your new balance is going to be $10,512.50, or expressed this way, it's going to be equal to 5,000 times 1.05 to the power of 2, which leads to the exact same number, 10,512.50. Right? So they both give you the same value. And at this point, we can start to see the pattern. Here we had 1 at the end of 1 year, and here we have this pattern. I'm going to put a 1 right there so we can see it. It's the initial investment times this number, and this number is 1 plus the interest rate, raised to the power of 1 because it's 1 year. At the end of 2 years, it's going to be 5,000 times 1 plus the interest rate, 1.05, to the power of, and then this guy is going to be a 2 there, right, because it's the end of the second year. So from here, we can pretty easily guess what's going to happen at the end of the third year. If I told you, hey, figure out what happens at the end of 3 years, what's the balance on the account going to be? At the end of 3 years, it should be 5,000, the initial investment, going back to square one, the initial investment, times 1.05, raised to the power of 3. Right, at the end of year 3 over here. The initial balance on year 3, I know, is going to be $10,512. Wait, what did I do? Did I do something wrong here? Ah, this is wrong. And nobody said anything, man. I need coffee. So $5,250 plus the interest earned is only $262. This should be 5,000. don't know what I was thinking. 5,000 $5,512.50. Can't believe you guys didn't say anything. Just let me go on and on and on. Okay, so then that part's right. That part's right. And then, of course, that means that the product of these two equals this number. Man, that'd be great interest if it jumped from 5,000 to 10,000 in 1 year. It's a little too aggressive. So this thing then should be $5,512.50. Okay, are we good now? Any questions, any questions, any questions? Good, okay, so the starting balance at the end of the third year is $5,512.50. And I know you're going to earn some interest, and that interest is going to be 0.05 times $5,512.50. So it's going to be 0.05 times $5,512.50. So you earn $275 with 60, let's round it up to 63 cents, 63 pennies. Good. And then you add these two together to give you your result. And I could add these two together, or I can apply this formula. So when I apply it, it'll be 1.05 to the power of 3 times 5,000. And let's just use our calculator on here. So launch, we'll use it in a minute anyway. Okay, so it's 1.05 to the power of 3. Enter. That's my answer when I have the 1.05 to the power of 3. And then that previous answer times 5,000 gets me to that. $5,788.25. Any questions? So that's what we get here. $5,788.13. Rounding. Good, good, good. Okay, so the value of a formula, as opposed to doing it the old-fashioned way, one of the great values is that we can jump ahead. We don't have to do every individual step. If I didn't have this formula and I wanted to find out what's your balance at the end of 3 years, you have to do it step by step, because you have to find out how much interest did you earn the first year. You have to get this $250. Then you have to add that $250 to the second year so that you can earn interest on that money the second year. Then you have to figure out this number, how much did you make in interest the second year, and you have to add that to your balance. So if I asked you to figure this out, you know, how much money will be remaining in your account, or what will be the balance at the end of, say, 10 years. Let's move this down. If I said, okay, let's just skip down the road here and see how much money is in your account at the end of 10 years. Well, doing it the old way, we'd have to do it step by step by step by step, because I need to figure out what is the balance at the start of the 10th year. Well, you can't figure that out until you figure out how much you earned the previous year, and so you have to know the balance on the account on the 9th year, then the 8th year, and so on. So doing it the old-fashioned way can take a really long time. It's a lot of work, and it's a lot of room for mistakes. But this great little shortcut here, this formula, helps us get to the answer fairly easily. It's just going to be 5,000 times 1.05 to the power of 10. That will tell me the balance on the account after 10 years if it earns interest compounded once a year at the end of the year, and the interest is given as 5% annually. Good. So now we can just type that into our calculator. Put that over here. Where is this guy? So 1.05 to the power of 10. So 10 years earning this interest rate, 5% interest rate, times your initial balance. Enter. You get $8,144.47. 81.44.48. Good. Questions? Is that what it was? Yeah, 47, I guess. 81.44. Any questions at all? 47. Okay, so that's the more sort of generic version of the formula, right? So far we have that if P is the initial principal, right? P is the initial principal invested, and we know that we have this formula here where we have 1 plus the interest rate, R, given as a decimal, of course, and then raised to the number of years, T, right? So this is the general formula for it. And that's assuming that, or this works fine as long as the interest rate is in years and this is in terms of years. Okay, but what if they're not in terms of years? Then it turns out that it's the exact same formula as long as these two things match. So like if they're giving you the interest rate per month and then they're asking you 3 months later, it's the exact same formula. They're asking you, after 20 days, what's the balance on the account if you are earning interest, and then they give you a daily rate, then that's fine. If these two things match, this is the formula. If they match. If they match. Good? Okay, so if they match, this is the formula. But what if they don't match? What if one of them is given in terms of month, every month, and this one is given in terms of, years? They don't match. Or this one's given in terms of days, and this one's given in terms of months. They don't match. So we have to adjust it a little bit. Luckily for us, it's not that complicated because rates are almost always given on an annual basis. It's almost unheard of to not be presented a rate that is not annualized, right? And that's just a decision that the federal government or somebody has made. I'm assuming a federal regulation, probably to make things a little easier, because otherwise I think people would be a little confused. If banks were allowed to give you rates that were not annualized, I think it would be pretty easy to confuse people. And trick them into thinking something is better when it's not, and it'd be harder as a consumer to make a good choice if the banks were allowed to give you rates at different non-annualized forms, because it's hard to compare and contrast. It's hard to really figure out things, and most people would get tricked. They don't know that much math, right? Any rate, so. Interest rates are almost always given as an annual thing. So when they don't match, this will be usually given in years, and then this will be given in some other term, like they say months, for example, but this one is in years, or this one will be in days, and this one will be in years again. So what we do is we make the match. What we do is we divide the rate by a value that will give us the rate in a form that will match the time frame here. So, for example, if the time is in months, for example, if the t value is given in months, then what we have to do is take the r value, which is per year, and then divided by the number of months in a year, right, where there are 12. So if we take the rate that's given per year, just to make it an easy number, let's say that they tell you it's 12%. Well, that's a little too obvious. Make it 24% per year, 24% per year, and they're asking you about something in terms of months. Well, what you got to do is you got to divide that 24% times 12, divided by 12, so you get the monthly rate. And then once you have the monthly rate, then you got to figure out, well, how many months are they, are they asking you about? Does that make sense? Sort of, kind of, maybe. Okay. So what matters is how often this interest is going to be compounded. Does that make sense? So even if they match, even if it's given to you in years and months, I'm sorry, if the rates match, if they're telling you that the compounding happens more often than once a year, then you have to make them match and have them match the time frame in which they compound. Good. Any questions about what I've said so far? No? Okay, so let's look at the formula in general, and we'll apply another example. So exponential functions occur in calculating compound interests. Okay, good. Principle, okay, so we have, this is very similar to the example I just pulled up. So to the third power, to the kth power. Okay, so here is the general formula for compound interest for various time frames of compounding. So if n is equal to 1, it means it's compounded once a year, which is the formula we just did, right? So if n, let's see, n equals to 1, then the formula becomes that the interest earned on the balance on your account when P is invested becomes just this, the formula we just figured out, right? That's when n equals to 1. When n equals to 12, compounded 12 times a year, this means monthly. Right? In 1 year, it gets compounded 12 times. It means it gets compounded once a month, right? Okay, so now the rate is going to be given to you in terms of years. So in order to get the monthly rate, we take the R value and divide it by 12. And that'll give us the rate per month. Okay, so that means that this guy right here now is the rate per month, interest rate per month. Put it down here. Okay, because R is going to be given to you in terms of rate per year, but if you're doing compounded monthly, that means that if you take that annual rate and divide it by 12, you get the monthly rate. And now you need to figure out how many cycles of the compounding must happen. So for example, if they asked you for 3 years, let's say t equals to 3 years, but now you've change the question to compounding per month, then that means that there's going to be 12 times 3 makes it 36 different cycles, right? Where you figure out the interest earned that cycle, you put it back into the balance, and then you multiply it again. So what we need to do here is to multiply this by 12 times t. 12 times t will tell you how many months, and now these things will match, right? So t is 3 years, that means there's 36 months. If t is 2 years, that means there's 24 months. And then that way these two things will match. We'll have a monthly rate, and then we'll have a time frame that matches the this rate, monthly rate and the number of months. So this would be the formula when n is equal to 12. Good. So in general, the formula is just based on n, the number of times that that your account is going to be compounded per year. Any questions on this formula? Anybody? Anybody? Okay, there we go. Good enough for now. Okay, so a sum of $1,000 invested at an interest rate of 12% per year. Find the amount of the accounts after 3 years if the interest is compounded annually, semi-annually, quarterly, monthly, and daily. Okay, so the rate and the length of time invested are presented both in years, so that matches. To begin with, that matches. That's in years, and this is in years, so that first hurdle is already there. If it was a real simple question that they said compounded annually, so that first one is n equals to 1. It's compounded annually. N equals to 1. Okay, this is annually. And why did it jump to such a thick thing? I don't know. Annually. Okay, so then our formula says that A of t is equal to the principal times 1 plus the rate to the power of t. So for us, that's going to be equal to 1,000. Principal was $1,000. 1 plus the rate, which is turned into 0.12, to the power of 3, which is 3 years. Good. So we get an answer from that. That's going to be 1.12 to the power of 3 times 1,000. I'm getting 1,404 and say 93 cents. Good. This is A of 3. Interest after 3 years. Okay, so then the next one was semi-annually, quarterly, and then finally monthly and daily. All right, I'm not going to do them all for the interest of time, so let's just skip around to, say, the daily rate. Let's jump to the last one. Oh, let's say quarterly. Quarterly means that it happens every 3 months, 4 times a year, quarterly, right? So this is the case where n equals to 4. N equals to 4 is quarterly. Quarterly. And so our formula becomes this: A of t equals to the principal amount invested times 1 plus, and now it's the interest rate divided by 4. The interest rate is annualized at 12%, but if we're doing it quarterly, we divide that by 4, we get 3%. So it's 3% every 3 months will get us to 12% per year, right? To the power of, and now we have to multiply the number of times we're compounding it per year, which is 4 times per year, times the length of time t. Good. So for us, we had 3 as the value of t. So that gives us 1,000 is the principal amount invested. 1 plus, and this was 12%, 1.12 divided by 4, to the power of 4 times 3. Or A of 3 equals to 1.00, not 1.1, comma, 0 times 1 plus 0.03 the power of 12. Okay, so 12% compounded annually, I'm sorry, an interest rate of 12% per year for 3 years, compounded every 3 months, that can be solved by doing this. Instead of 12% per year, it's 3% per quarter, per 3 months of the year. with 12 cycles. There will be 12 cycles, 12 quarterly cycles in a 3-year time frame, right? So the compounding will happen 12 times. Good. Okay, so now we can just punch that into our calculator, and we see we get a slightly different number. So it'll be 1.03 to the power of 12 times 1,000. We get $1,425.76. Any questions? No? 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 Okay, let's just look at a table with all the other values. Let's make sure we match for ours. Here is a table that has all of them, a nice neat thing. So for annual, n was equal to 1, right? We just replaced the n with a 1, and we end up with this, which is exactly what we had up here, $1,404.93. For quarterly, we replaced the n with a 4, and we end up with exactly what we had up here, $1,425.76. Good. Say, for example, monthly, we replaced the n with a 12. So that means that instead of getting 12% per year, we're getting 1% per month for 36 months. Good. Compounded monthly. $1,000 invested at 12% per year for 3 years. You're going to get the same answer as saying $1,000 invested for 3 years, compounded monthly. So you get a monthly rate of 1%. A monthly rate of 1% for 36 months is the same thing as saying a 12% annual for 3 years, compounded monthly. Good. Any questions? No? 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 Another case. A sum of $1,000 invested at an interest rate of 12% per year. Find the amounts in the account after 3 years if the interest is compounded. Wait, did I just copy? It's the same question as that one, so I don't know. It seems weird. Okay, so if investment earns compound interest, then the annual percent yield is the simple interest rate that yields the same amount at the end of 1 year. Okay, so it's kind of like the equivalent amount. So it makes this interest rate makes it easy to compare different offers, right? So if some bank offers you an interest rate that's compounded monthly, another bank offers you a different rate that's compounded every 3 months, you know, how do you compare them? How do you know which one's better? Well, it's just simpler to figure out what would be the simple rate equivalent that would give you the same amount at the end of 1 year, and that's the annual percent yield. Good. So, for example, find the annual percent yield for an investment that earns an interest rate of 6% per year, compounded daily. So we know that our formula is going to be equal to this. It's going to be equal to the principal amount times 1 plus the rate, r, divided by n, to the power of nt. So then this guy, let's put it below. This guy is going to be equal to so this guy is going to be equal to the initial investment. Come on. Times 1 plus r divided by 365. Oh, r is given to us as 6%. So this is going to be 0.06% divided by 365 days in 1 year, approximately. Not quite exactly true, right? It's like 365.25 days in a year, which is why we end up having a leap year every once in a while. I don't know if you guys knew this, but we didn't really account for that in our calendars for a long time. So we kept like falling behind over the centuries. The centuries went by. The weather would no longer match what we thought it would be, right? Summers are all of a sudden cold and winters are all of a sudden warm because we kept falling behind a quarter of a day every year 4 days, every four cycles. So over centuries, we kept falling behind until we finally readjusted our calendar for it. So one day, like in the 1300s or something, we just skipped like a month in the calendar. It just like disappeared. Wait, was it in the 1300s? Forgot when it was. You can Google it. It's pretty interesting. At any rate, 365 times t. And they give us t per year compounded daily. Find the annual percent yield for an investment that earns interest at a rate of 1% compounded daily. All right, well, so let's make t equal to 1, say for 1 year. Then this guy would be equal to 1 right here. Okay. And then this is just some number we can figure out. So this is going to be p times whatever this is. So 0.06 divided by 365 gives us this tiny little number plus 1. So I'm getting, this is 1 plus 0.1230, 164 to the power of 365. Oh, come on. 4 to the power of 365. Good. Okay, so then we just figure out what that is. Power of 365. I get p times 1.06183. 1311 if you want to be a little more accurate. Okay, so the principal amount multiplied by this decimal right here will be your interest at the end of 1 year if you have 6% annual compounded daily. Now, if you want to find the equivalent amount, right, an equivalent offer that's just annualized, then the formula would be really easy, right? So over here, I'll put it over here. If n was just equal to 1, compounded annually, then the formula would have been really easy. It would have just been p times 1 plus r raised to the power of t. So at the end of 1 year, t is 1. This would have been p times 1 plus r to the power of t, right? Where this r is the annualized rate. That's equivalent to this, and compounded once at the end of the year. Okay, so we match these up. So t is equal to 1, since we're just letting t equal to 1 year to compare these two. That's just a 1. So when we set these two things equal to each other and solve for r, this is going to be p1 plus r. Then we divide both sides by p. Divide this side by p. Divide this side by p. Both of the p's cancel. And we're just left with this 1.06. Come on. I think this file is too big now. 1.06183 equals 1 plus r. So if we subtract 1 from both sides, we get this 0.6183 equals to r. So there's our answer. 6.183% is the equivalent rate, annualized rate, this is per year, per year, compounded annually, that would give us the equivalent amount. Does that make sense? Any questions? Any questions? Any questions? $61.83, is that what we got? Yeah, 6183. Okay. Let's take a break here. So this is the end of section 1 in chapter 4. Let's take a little break here, and we'll be back and continue with 4.2. Okay, section 2, chapter 4. Moving on to the natural exponential function. So in this section, we're going to cover the number e, a very, very important number in math, in calculus, in just about everything in our lives, really. A lot of stuff. Like, there's a few things in math that are kind of niche and don't really impact our lives in many ways, but e is definitely a very, very impactful development in math. It has far-reaching implications, and it's really knitted into our fabric of science in a lot of different ways. So it is really, really important. We're going to look at the natural exponential function and then continuously compound interest. So first off, e. What is e? How do we get to e? Let's consider e. Okay, so any positive number can be used as a base for an exponential function, right? Going back to the formula for an exponential function. Remember that the formula we were looking at was just, say, f of t. Why is this thing in the most thick? Okay, f of t equals to some base a to the power of t, right? Akin to f of x equal to a to the x power, where a was the base, and it could be any number that was strictly bigger than 0, right, to infinity. However, we also skip the number 1, and we skip it just because it's boring to have 1 to the x power. Okay, but it could be any real number at all, right? That's what they're referring to here when they say that any positive number except 1 is considered to be the base of t, the base of this exponential function. Okay, so we're going to consider, how about if we let that base be the number e? So before that, let's consider what is e and how do we get e. Here is e. E comes from, well, there's a few different ways to develop the number e, but here's one of them. It starts off by thinking about what happens with this function right here. So if we think about the function, say consider the function f of n, right? So the input is n. F of n equal to 1 plus 1 over n raised to the nth power, right? So that's a function we're going to think about. Some brilliant person long ago was sitting around on a Saturday night thinking about this function, right? What else do you have to do? What better thing to do is there to sit around thinking about interesting functions? So he thought about this one, raise the power of n. So let's say n was equal to 1. Then that means that this would turn into 1 plus 1 over 1 raised to the 1 power. Good. So that would just be 2 to the power of 1. So then the first number is just 2. Good. Okay, what if n was 2? N was 2. Then we would have 1 plus 1 over 2 raised to the 2 power. One plus 1/2 is 1.5, which is 3 over 2, raised to the second power, which makes it 9 over 4. 4 goes into 9 2 times. What the heck is that? 9 over 4 which gives you 2 1/4 or 2.25. Okay, so that's the value we get when n equals to 2. Let's do one more, 3. What if n was 3? Okay, so we have 1 plus 1 over 3 raised to the third power. Okay, so this is going to be 4/3. Right, that goes into it 1, and then 1 remaining makes it 1 1/3, which is what this is. Raise the power of 3, which makes it 4 to the third power is 64, and 3 to the third power is 27, which makes it, okay, this time I'll reach up for a calculator. 64 divided by 27 is going to be 2.37, 2.37037, and so on and so forth. So it's really 037 barred. Okay, and then we would keep going, right? What happens when n equals to 4, and what happens when n equals to 5, and what happens when n equals to 6, right? So we got to keep going, dot, 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 dot. And what we want to explore is what happens as this n value goes down, 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 goes toward infinity. That's the pattern we're looking for. Okay, it's kind of hard to see initially, so you really have to think about big numbers going forward is what we want to look at. So let's use Excel to try and see where that goes, and hopefully my computer can handle that. If not, we'll skip it, but let's see. So I'm just going to use Excel to repeat that little table I had just created, exact same thing. I'm just going to put it on here so that we can do it faster. So we have a column that's going to be the n values, like 1 and 2 and 3, for example. Right? And then we have this other column, which is the actual function, and it was going to be 1 plus 1 divided by n. Right? And then the whole thing is raised to the power of n. Good. So this is the equation now. F of n equals to 1 plus parentheses 1 divided by whatever's in this box, close parentheses, to the power of whatever's in this box. Correction, no, go away. Okay, go away. So I want to raise the whole thing to the power of that guy. That should fix it. There we go. Okay, so that's the same answer we got for the first one. And then here are the first 3 that we got. Let me make this bigger. Let's say we go out to about 20. That's not a good sign. It's already slow. That's definitely not a good sign. Okay, so we'll just do it for a little while, see how far this goes. Okay, so let's make this equal to the previous number plus 1. And then this number is going to be equal to that number. And then these two are that. Okay, so here are the first 3 numbers, just like we did it in our table. But now the system is set up so that I can just extend this a little bit more. And now I automatically get what happens when n equals to 4. When n equals to 4, we plug it in here. We end up with 1 plus 1/4 raised to the 4th power. And then we end up with 2.44. Okay, and then we keep going. How about if we do it to the 5th power? That's going to be that one. And what if we do it to the 6th power and to the 7th power, okay? But again, we care about very large numbers. So let me skip on down and do this for a lot of numbers. I hope my computer doesn't crash. Okay, so keeping track of the value of n, look at what happens to the output, right? Obviously, we always start off with a 2, but then the first decimal after the 2, the first decimal was a 2 first, then a 3, then a 4, then a 5. So let's keep track of that first decimal after the 2. Right now it's at 6, 2.6 something. And then it says 7 now, 2.7 something. So what happens with this formula is that it's always growing. It's growing, always growing. However, the speed at which it grows begins to slow down. And so as we go farther and farther out, the first few digits become more and more stable. Right? Obviously, we always start off with a 2. And then the first decimal value after the 2 is eventually centers into a 7. And then it doesn't change after that. And then after a while, the 1 becomes pretty constant after the 7. So it's always 2.71 something. And it looks extra weird because sometimes it changes values. But anyway, so then after the 1, there's a 6 at the moment. And if we keep going through this, eventually that might change. Okay, so this is, I'm going to stop here. This is after n equals to 774. The first couple of decimal places are already pretty constant, right? It's always 2.71 something, 2.71 something. And if we keep going way down here, eventually we might see, look, it's about to change from a 6. It's getting really close to change from a 6 to a 7. So now it's 2.717. Okay, so that 7 wasn't quite so stable. But if we keep going, where is this heading? Now this looks a little weird because sometimes we have more decimal places, sometimes we have less decimal places. Let's make a couple of changes up here. First of all, let's set this, let me set it to a specific number of decimal places. Where's the... format cell. Ah, shoot. That's not what I wanted. Format cell. I want it to be a number with .30 decimal places. And let's extend that to here. Okay, so, the computer quits after a while. So there's going to be a lot of zeros at the end, not because it really is zeros at the end, but because the computer, not necessarily because it's zeros at the end, but because it's more likely that the computer just doesn't have that much computing power to go out to that many decimal places. But at least this way it'll be a little bit more consistent. And also, I want n to go really big. So instead of jumping by ones every time, I'm gonna change this so we're actually jumping by hundreds every time. Let's do that. So let's see, can I extend this up? Oh, I didn't like that. Can I extend this thing up? Yeah, that works. Okay, so let's change this so that it changes by 100 values every time. Right, so it went from 100 to 101, and then I want to go to 201, to 301, to 401. So I'm going to be jumping by hundreds. That way I really let n get really big really quickly. So now let's extend this out. For a little while. Not too much, since my computer doesn't really go that far out. Alright, hopefully that's catch up. Okay, so now we see that n is really growing quickly. If we jump to n equals to 101, this would be 1 plus 1 over 101 raised to the power of 101. And then here, this is the case where n is 501. 1 plus 1 over 501 raised to the power of 501. Now we can really see what happens to the outputs, right? So obviously we start off with a 2, and that first whole number value is always 2. That doesn't change. The first value after the 2 pretty quickly locks in on 7. Remember when we were doing 1, 2, 3, 4, 5, it didn't lock in on 7 right away. But now, since we're jumping by hundreds, we can see that that first decimal place is pretty much locked in. Okay, so as we let n grow bigger and bigger and bigger, we see that the first few decimal places are pretty locked in. It's always a 2.71. The 1 is already locked in. The 8 looks pretty locked in at this point. The number after the 8 right now is a 2. And that one at the moment seems a little stable, but the one right after that is still changing pretty quickly, right? So the 4th, 5th decimal place at this point are still pretty actively moving. And remember that as n gets bigger and bigger and bigger, this will always be growing, but it keeps growing at a smaller and smaller amount. So the further out we go, the more we lock in on some value. Okay, so the point of all this is that we wanted to study what happens as this function goes out to infinity. Where does this head? And it heads to the value we call e. Okay, so eventually that 2 that's after the 8 will lock in on a 3. So it'll be 2.7183 and then dot, 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 dot after that. So e is what we call an irrational number. It's a number that goes on to infinity and never repeats itself. There's no pattern to its repetition. If we kept going through this, if we had a really powerful computer and really went to town on this and really pushed a very, very high value of n, we would get an even better approximation of what e is. But of course, we would never get the complete approximation. The complete exact answer. But if we kept going, eventually we would see. Here's a little table similar to it. So here's a table similar to what I created. At 1, we had a 2. At 5, we get this decimal. At 10, this decimal. At 100, that decimal, and so on and so forth. But eventually, it starts to narrow down on this. Oh, and I was wrong. This doesn't move to 3. It stays at a 2. And then the next decimal place that kind of locks in is an 8. Okay, so we got to keep going, though. This is not e either. There's no way to actually write down e. We just got to keep going, right? And if we kept going, we get more and more and more decimal places of accuracy. This is when n equals to 1,000,000, we get this number. So if we let n grow even bigger, we'll end up with an even better approximation. Good. There are kind of contests in the math world for people to figure out a larger approximation to this. So if you build a computer that is purely dedicated to do what I just did with Excel, and then really push the outer limits, then you can win this contest. So I believe that at the moment, again, this is something you can Google, I think at the moment they're in the like 50 billion decimals kind of area for the winner. So this one is accurate to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, right? This is accurate to 20 decimal places. The current winner of who's been the most accurate, I think they're in like 50 billion decimals area. I could be wrong, but yeah, Google it. It's pretty interesting. I mean, I'm sure they must have created a computer purely dedicated for this and had it running for like months, I'm sure, in order to reach, those high levels of specificity. But for us, we don't need that much accuracy. It's good to know the concept of how we get it, right? It's this number that we can't really write down the actual exact number, but we can be as accurate as we want, depending on how many n values you want to use. For us, we normally are fine with 3 or 4 decimal places of accuracy, for the most part. But if you really want to get more accurate, then you can get more decimal places of e. You can get as many as you want, depending on the value of n. Good. Any questions at all? No. I still haven't answered why we care about this. This is just fun for now, obviously. But why do we care about this? Why is this such an important thing? That's to be discovered. It is a very important number. Okay, the number e is based on the natural exponential function. Why use such a strange base for an exponential function? It might seem at first a base such as 10 is easier to work with, right? Base 10 is easy to work with because we have a base 10 number system is what we're used to, right? We have a base 10 number system. Why do we have a base 10 number system? Because it takes 10 unique little figures to make up our numbers, right? We've created them with 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 0 is the other one, right back here. There are 10 of them. If we count these, there are 10 of them. And then all other numbers are created by combining these in one way or the other, and where the order matters, right? 4, 5, 6 is 456, 6, 5, 4 is 654, right? So we recombine these, and the length makes a difference, and the order makes a difference, and we toss in the decimal place and commas, and we can express any real number, any rational number that we want to express, right? So we use base 10. I know that we're all incredibly comfortable with these. We've seen them all our lives, so it almost seems like second nature that, of course, there's 10 of them. But if I was going to invent my own number system, maybe I decide to make it base 4. Maybe I decide this is one number, and then this is two numbers, and then maybe this is another number, and maybe this is another number, right? Maybe it's base 4, and then all my numbers would be based on this, including the order, right? So the next one on my list might be, if I was creating my numbers, the next one on the list, instead of coming up with a brand new picture to describe the next one, I might just recombine these in some order, right? Next, you have to get the one with the X like that, and this one, and that's the next number on my list. And the next number after that, maybe it's, I don't know, maybe it's this one, again, repeated, and then this weird, maybe this one with this one, 2 dots on there, right? Maybe this is my next number. I don't know, right? I could keep going, but some way of reorganizing and recombining my original 4 numbers, these original 4, if I kept going, and the reordering of them and maybe tossing in a decimal would allow me to come up with all numbers, then this would be a base 4 number system. But we have a base 10 number system. And so because we have a base 10 number system, 10 is often full of really great outcomes. And why does this thing keep popping up? So it's really convenient to do things in power 10. Go away. Scientific notation, for example, is very useful for that reason. Anyway, but now, out of nowhere, we're suggesting that this value e is just as useful, just as important, and we will see why, right? It comes up a lot in calculus, and it's really fundamental to a big part of calculus, so it's really important. So we're allowed to have any base, so we're going to let e be the base, right? So when you see this, mentally you can think of converting it to its decimal approximation. Remember that e is approximately 2.7183 is usually rounded to that, approximately. And these little wiggly equal signs means that it's approximate. So when you see this, you're really being asked, really being asked this. It's 2.7183 to the power of x. Right? So think of it as any other base number raised to an exponent. What is up with my computer? Why did it jump to there? Okay, so let's compare it to other functions. Remember that the graph of any exponential function where the base is bigger than 1 is going to have this sort of a shape. For x values that are greater than 0, it's going to grow up toward infinity. And for base numbers that are less than 0, negative values, it's going to grow down or push down toward 0. Let's use Desmos to demonstrate that. So remember that if we had y equals to 2 to the power of x, we have this kind of a shape, this kind of a graph. It goes through the point 0, 1, because 2 to the 0 power is still 1. And then if we let x be a 1, we have a 2. So it goes through the point 1, 2, right in here. Right in, come on, get in there. There it is, 1, 2. Good. And then if we let x equal to 2, then we get the point 2, 4, which is right in there. Good. On the other hand, if we let x equal to negative 2, the negative flips it upside down, and so we end up getting 1 over 2 to the power of 2, which is equal to 1/4. That'll give us this number right here. When x equals to negative 2, we get 1/4 as the output, or 0.25. Is that okay? Any questions about that? Okay, so we saw that whenever y has a base that's bigger than 1, we're going to get this same shape. So if y was equal to, I don't know, how about 5 to the power of x, then it has the same sort of shape, except that for the positive numbers, it'll grow to infinity a little bit faster. And for negative numbers, it'll grow towards 0 a little bit faster. So that's what happens with that base values. We let it be some sort of slider. Let's let that be a. A is a slider. And let's let it be equal to 0.1 to, I don't know, 10 by 0.1 numbers. And so here's 2, come on, here's 2. So when a equals to 2, we have that 2 to the x power, and as it gets bigger, so here it is when a equals to 3, it has that shape. When a equals to 4, it has that shape. When a equals to 5, 6, 7, 8, 9, 10, right? So it gets bigger and bigger and bigger and bigger and bigger. And then the shape, it stays the same shape. It always goes through the point 0, 1. And then the same pattern occurs that on the positive end of the domain, it'll grow toward infinity faster and faster the bigger the base. And on the negative side of the domain, it'll grow towards 0 faster and faster. Note that the output is never equal to a negative number. Right? The output is always positive. And the output is never actually equal to 0 either. It gets infinitely close to 0, but never actually 0. Good. Okay, so I get to punch in whatever number I want as the base. Here I'm going by multiples of 0.1 and skipping through these values. But it can be anything, so I can make it be equal to 2.7183, the value of e, to get a pretty good approximation. So when y equals to 3 to the x power, we get that purple one. So we know that the one we're looking for is going to be somewhere in between those, right? Because e is somewhere between 2 and 3. So it's equals to e to the power of x. Oops, the power of x. So it's this black one right here is the one we want, right? The red one is 2 to the x power. The purple one is 3 to the x power. And as you can see, the black one on here would be e to the x power. It has the same shape. And if we wanted to create a table, we can find all those same values that way. So let's, for example, create a table. Oops. X and e to the x power. Okay, so at 0, you're still going to get 1. Still goes through that. And at 1, that would be e to the 1 power. That's just e, 2.718. Good. When we have 2, then we'll have 2.718 squared, which turns out to be 7.38. Okay, and that's what this little dot right here is. Good. When we let this be 3, then it's going to be 3 squared, which is going to give us all the way out to 20-something. So that's going to be over here. Here it is. 3, 20.086. Here is 2, 7.389. Here is 1, 2.78, and then 0, 1. And then, of course, if we let n equal to -1, we'll get 1 over e, which then gives you approximately this value, 0.3678, which will be like that guy right in there. Good. So slowly we get to see the shape of the graph of e to the x power. Any questions? No? Good? Sort of? Kind of? Again, we still haven't explained why it's so important, but it is. We'll get to why it's so important in a little bit. Okay, some expressions. So evaluate each expression, round it to 5 decimal places, and the intention here is to use your calculator. So just to make sure you know how to use your calculator. So let's use the calculator. Can I already have it open? Oh, thought I did. So we have a special magical button on our calculator that's E, because it's really important. So rather than typing in the approximation, 2.7, we can just use the value E, the number on our calculator. And the E button is right above the division button, right there, the little E. Okay, so if we type in second and then that button, and we get the little E, and if we hit enter, we'll get the actual number, 2.718281828. And then this is just what is being displayed. I believe the calculator internally has it out to more decimal places than this. So this would give you a very nice, very, very close approximation to your outputs. So let's do the first one, which is e to the power of 3. So there's our answer to the first one. E to the power of 3 should be 20.085536, that guy. Good. The next one, let's put 2 times, and I'm going to put it in parentheses, e to the power of, and then it's -0.53, and then close parentheses, and enter. So I get that guy. It's such an important value, e, that they also gave you a second shortcut for e. Here I'm kind of manually putting e to the power of, but they also gave you the function e to the power of, which is over here. So we can also use that one, right? So we can hit second, and then this guy, and that automatically skips the one button that says to the power of. So I don't know how much of a shortcut it is, but it's a bit of a shortcut. So we can just put 3 there, hit enter, we get the same answer. Or second, and then e to the x, and then put in -0.53. Right, we get an answer, and then we want to multiply that answer times 2 to finish out our thing. So we can hit 2 times, and now you can manually type in 0.5886. You can do that. Or we can use this button here that says answer, and that'll be the previous answer recorded on your calculator. So hit second, answer, and then it'll automatically be 2 times this result there. So we get that. Good. And finally we had second, oops, we had e to the 4.8. Any questions on how to use your calculator to approximate these values? No? Nobody? Nobody? Good. So same results we got from my calculator. Any questions, any questions, any questions, any questions? Okay, one of the reasons E is so important is because it appears a lot in nature. one of the important aspects of math, one of the reasons we study math, is because it helps us understand the world around us, right? So there's a big application part of math. It's not the entirety of math. Uh, it's just one facet of it. We're trying to understand how gravity works. We're trying to understand how genetics works and how air around the surface of a wing functions, and all these things that we're trying to understand. And we can come up with mathematical models that either exactly explain how it works or give us a pretty good approximation. And so when we're trying to come up with these models, these explanations for how the universe works, often we find that this special number e becomes very useful in either giving us the exact model, the exact equation that describes exactly how it works, or at least a very good approximation. An approximation that is so good that it is almost equivalent to knowing the answer itself, right? When you're trying to understand the flow of air around a wing, it would be great to understand an exact equation that that definitely tells you exactly what the answer is. But if you come up with an equation that is good to 30 decimal places, that's probably good enough, right? So the area of math is pretty big, pretty diverse, but the applied math part of it usually focuses itself on coming up with mathematics that helps us define the world around us. The other side, that's more theoretical math, doesn't necessarily care too much about that. The other reason we study math is because it helps us become rational thinkers, good puzzle solvers, and we have found, over the course of public education, that it's a really good way to get people to become better puzzle solvers, good rational thinkers, to be able to apply that sort of thinking to other areas in their lives. So it's something we push for that reason. Everyone should learn math for that reason. But then there's also this applied side. Okay, so here's an example. When we try and describe how viruses flow through a population, the number E appears in the models that do a pretty good job of describing it. So here is a case. An infectious disease begins to spread in a small city of a population of 10,000. After T days, the number of people who have succumbed to the virus is modeled by this function, right? So V of T is going to be the number of people who have succumbed to the virus after T number of days. So here is the entire population, and here is this thing here. So let's look at the first case. How many infected people are there initially at time t equals to 0? So this is a pretty easy example, really, where all we have to do is plug in, or this is a plug and chug question. Unfortunately, it's not more interesting than that, but we'll try and come up with examples that are a little more interesting. Okay, so this one's just a plug and chug. So all we have to do is replace that t value with a 1, and so we get this, 12, 4, 5, times e to the power of negative 0.97, and then we want to know what happens when this is a 0. And t equals to 0, so we multiply this by 0. Okay, so if we multiply this one by 0, then that means that whole thing is going to be 0. And e to the power of 0 is 1. Good. So then 1 times 1245 is 1245. And 1245 plus 5 is just going to be 1250. So this one ends up being 10,000 divided by 1250, which ends up being 10,000 gives you 8. Okay. So according to this model, this is saying that at time equals to 0, at the very beginning, beginning, there are 8 infected people in this population of 10,000. And then, of course, they're going to begin to infect others, and then the people they infect others, and so it begins to grow exponentially, right? It's a pretty popular phrase, exponential growth. Okay, find the number of affected people after 1 day, after 2 days, after 5 days. Okay, so all we have to do is replace this 0 value with a 1 to see what happens after 1 day. Replace this 0 value with a 5 to see what happens after 5 days, and so on and so forth. So let's just see like a table of that. I think it's down here. Here's our solution. So we replace it with a 0, and we get an 8. And then we can use a calculator to find the rest of the answer. So here's a table for that. And remember, the formula for this whole thing was V of t equaled to 10,000 divided by 5 plus 1245 times e to the power of negative 0.9, what is it? Negative 0.97. T. Okay, so if we replace the t with a 1, we'll get this number. We replace the t with a 2, we'll get this number. Replace it with a 5, we'll get this number right here. So let's use a calculator. It says using a calculator to evaluate all these things. So let's practice doing that into our calculator. And we're going to do it by, well, obviously we can just type it all in. You know, when some of you are very new with these calculators, so I would recommend that we start off with the denominator, figure out the most complicated part, which is this, and kind of peel it away from the inside out, figure out what this is, and then times this, and then add 5, and then 10,000 divided by whatever answer you get in there. So let's just do it for 5, for example. So V of 5 is going to be 10,000 divided by 5 plus, don't worry about that 18, 5 plus 1245 times e to the power of negative 0.97 times, and so we're going to do 5 and 5. And so we definitely want to use technology here. This arithmetic is pretty ugly, so please don't be afraid of technology. All right, so let's get over here, correct this thing. Okay, so to unravel this whole thing, let's put it over here. To unravel this whole thing, I'm going to start off with the exponential part of it. So clear, I'm going to start off with e to the power of, and then this product, which will be negative 0.97 times 5. I'll get an answer from there. And then I want to multiply that answer. So now if you just jump ahead, another little shortcut, if you just jump ahead to the operation symbol first, it'll automatically assume that you mean the previous answer operation. So I could hit previous answer like we did before, times, or something like that, times 7 or something. In this case, times 1245. Or I can just hit times, and it'll automatically assume that I mean the previous number, the previous result from our calculator. So that would be e to the power of this, and I want to multiply it by 1245, get an answer. And then again, I'm going to jump to the operation, plus, and it automatically assumes it's the previous number, plus 5. And then again, I'm going to do 10,000, 1, 2, 3, 4, 10,000 divided by the previous number, second answer, enter, and I get 678.13, right, approximately. Remember, this is a model, it won't be exactly the same. 678.13, okay, 678, approximately the same answer that we get from here. Good? Questions? No, 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 no. Okay, and then finally, let's do a graph for these. And you can do a graph on your calculator. If you do a graph on your calculator, then you're going to go over here, y equals, and then type it into here. You know, it's not so easy. You have to be really careful about parentheses and all that when you type in this whole thing. And of course, your calculator is going to do it in terms of x, not in terms of t, since every function in your calculator will be in terms of x. So just make sure you type it in all and be careful with all the parentheses. So 10,000 divided by parentheses 5 plus parentheses, and then the 1245 times, and then it's e to the power of, and then negative 0.97x, and then close these parentheses and close the other parentheses, and that should do it. Okay, that's pretty ugly. And then you can hit graph. So let's see, let's go to window. Let's choose from negative 10 to 10. And then the by ones, the output, let's go from negative 10 to, that's going to grow pretty quickly. So let's, I don't know, what does 1,000 look like? You can always come back and change this. And then go to graph, and there it goes, there it goes, there it goes, and boom, there's our general graph. Any questions about this? No? No? If I wanted to change the window, like maybe I want to see what happens over here, I want to go even bigger, then I'd have to go back to my window and change the Y maximum to be something even bigger so I can see it. So 1,000 wasn't big enough. How about 10,000? 1, there's 10, 1, 2, 3. Enter. Graph. So now we see this, and wait a minute, look, it was growing, 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 but then it didn't keep growing forever. It kind of reached some sort of plateau max, and then we don't know what happened, right? So it cut off. And I don't really care what happens over here. Remember, t is the number, is a time, so we don't want negative time. In this context here, we probably don't care about negative time. So let's go back to window. Let's change this from 0. Let t start at 0. And let's go out further out. How about, let's make it twice as much. How about that? And also 10,000 turned out to be too big. How about we make it, I don't know, how about 6,000? Okay. So it goes up, it reaches some max, and then it kind of plateaus out. Okay. Good, 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 good. Okay. Studying this graph, why would that be? As the input grows bigger and bigger and bigger, this goes out toward infinity, this is going to get very, very large, bigger, 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 and bigger. As this gets bigger and bigger, bigger and bigger, then multiplying it by a negative is going to grow toward negative infinity. So this is growing toward negative infinity times this number, e to the power of negative infinity. So this thing is growing toward 0. And so as this goes out to infinity, this is getting smaller and smaller and smaller and smaller. And so as it grows toward infinity, this is growing towards 0. 5 plus 0 equals to that, 5. So 5 divided by 10,000 is 2,000. So it looks like this is going to plateau around the 2,000 mark. So let's graph y equals to 2,000, and you'll see that. It kind of plateaus around there, around 2,000. Any questions about that? No? No? Let me write down what I said verbally on here. If you think about the limit, and maybe this might be new notation for some people. This is the limit as t grows toward infinity, right? As the function goes out to infinity, as the t value goes out to infinity, we want to explore what happens to v of t. Right? That's what we want to do. Okay, so as t goes to infinity, then e to the power of, let's just start over here. I'm just kind of breaking it down. Negative 0.97 times t, then as t goes out to positive infinity, it's getting bigger and bigger and bigger, multiplying a really big positive number times negative 0.97, this thing is going to head toward negative infinity. Good. And as this grows toward negative infinity, then e to the negative 0.97 times t, well, then that's going to grow toward e to the power of negative infinity, which grows towards 0. Right? So as I plug in bigger and bigger numbers for t, this part will grow toward negative infinity. E to the negative infinity grows towards 0. And now, as it gets closer and closer to 0, then the multiplication of a tiny little number close to 0 times 1245 is still going to grow towards 0. So 1245 times e to the power of negative 0.97t will also grow towards 0. Therefore, 5 plus 1245 times e to the negative 0.97t will grow toward 5. Right? This part will get smaller and smaller and smaller as t gets bigger and bigger. We contribute less and less to the addition of 5. Eventually, it's pretty close to just 5 by itself. And so, as t goes to infinity, that division of 10,000 divided by this whole ugly thing, 5 plus 1245 e to the negative 0.97t, the whole thing just kind of grows toward 10,000 divided by 5, which is where we get the 2,000. Okay, so as t goes to infinity, this whole ugly fraction begins to approximate 2,000. This right here is the line y equals to 2,000. So this virus spreading through the population looks like it plateaus around 2,000 people out of the 10,000. So it looks like it's going to affect a maximum of 20% of the population, right, as t goes on to infinity. Why that is, I don't know. It's something special, particular about this virus. Maybe it has to do with the population itself. Maybe certain people are going to be immune to this virus, and so not everyone is going to be affected. Maybe this takes into account the resolutions that the city will take in order to prevent the virus. Who knows? There's all kinds of reasons, right? So we're not really explaining why that is. We're just coming up with an equation that seems to do a pretty good job of modeling the growth of a virus, right? Obviously, we're in the middle of coronavirus season, so we're working really hard to come up with equations that describe this sort of thing right now. How is this virus spreading through our world? And of course, it greatly varies from region to region. In some parts of the world, it's growing very, very quickly. And in some parts of the world, it's not growing very quickly at all. And that's due to a variety of reasons for why it's worse in some parts and not as bad in other parts. Some of it is, of course, due to genetics and population, the age of the population, and the health factor of the population. Right, the virus will spread faster in a region with a bunch of sick people than it will in a section that has people that are very, very healthy and maybe naturally fight off the virus more. So it varies, and we're trying to come up with equations that model that as best we can. But the best we could do is an approximation. Right, there's just too many variables, too many unknowns. It varies a lot from region to region. So we come up with general approximations that do a fairly good job overall. Okay, any questions? Good. Also, the shape of the growth is given by this graph. That's what's another thing that's really nice. We can see that at first it grew pretty fast. Well, it started off a little on the slow side as t went out to infinity, right? So at first it wasn't growing very quickly, and then it hit its stride, and then it grows really fast, really super fast. It's growing at a very fast rate around there. And then as we begin to approach its max of 20% of the population, it begins to slow down. There are less people that are susceptible to this virus until we slowly approach the 20% mark. And at some point, we get to a point where no new growth will occur. Good. In terms of coronavirus and a virus growing into a population, that's what we call herd immunity. When there are no more people left for the virus to infect, and so we get to a point where the virus is like a hot potato getting passed from person to person to person to person, and when you get to a point where there isn't many new people in the population for the virus to infect, then as a herd, as a population, it found its immunity for the virus, so the virus then begins to die off since it doesn't have anybody new to infect. And the way to get to that will be to infect a bunch of people, and then those people either die, and if they survive, they have antibodies toward the virus, so they're less susceptible to getting the virus a second time. Some people are likely just going to be naturally immune to it. Their body will just fight it off. So there's people that are naturally immune to a virus. There are people that develop this immunity through antibodies. So they get sick, but then they recover and they have the antibody. Eventually, we'll figure out a vaccine for it. So some people will be vaccinated. But vaccines are usually not 100% or even close to it. So if we can, we're trying to aim for a goal of getting a vaccine that's approximately 50% effective. So if you get the vaccine, then the odds of you getting the virus when you're infected, when you're surrounded by someone who's infected, would be lowered. That's our goal. So even when you get the vaccine, you won't be 100% covered. It's not like you can get the vaccine and then you're like, aha, I'm cured, I can't get the disease, and now you can walk around and do whatever you want. That's not true. It'll lower the likelihood of you getting the disease, but it won't make it 100%. But the benefit of that is that it reduces, on the other side, the likelihood that the virus can spread. So you're just, again, removing the number of people, slowly reducing and removing the number of people that can get the virus in the population, therefore slowly reaching that herd immunity and getting to a point where the virus has nowhere new to go, and then it dies off, right? It's like a fire, a forest fire going through the forest. It needs new trees every time to grow, right? Once it burns down that tree, the fire would burn down, except it needs to jump to a new tree, a new tree, a new tree. So the way we fight forest fires is not that we directly put out the fire. We don't have enough water for that. So what we do is we try and see where the fire line is heading, jump ahead of it, chop down all the trees ahead of it, and make a clearing so that the flames don't have a new place to go to, and then they kind of burn themselves out, right? So that's sort of the same idea here. We're trying to get to a point where we remove enough people from the population that are susceptible to the virus so that the virus has nowhere new to go to, right? And a vaccine will help in that fight. It'll remove some people. If it's only 50% effective, then it'll remove 50% of the people. That's half as many people that are now susceptible to the virus. Of course, there'll be a lot of people that refuse to take it. So even if we get a 50% effective vaccine, you gotta create it, disperse it, people have to take it. It might be a several step process where you have to take it once and then 1 month later come back and take a second shot. And then of course some people will take the first shot and they won't come back for the second one. There's all kinds of complications that go into that, so it won't be like a one-shot clear and fix everything. It's something that helps us slow down the virus and get to a point where eventually it runs out of people and hopefully dies off. So anyway, I don't know, it's a random rant, but I figured it was applicable in our current environment. Any questions on anything? No? No? None? None? Okay, continuously compound interest. Remember that our formula for compound interest, we said that the formula was this guy, A of t, the balance at t years was equal to the principal invested, 1 plus r to the nth power raised to the power of nt. It was like that, right? And so we thought, okay, what if n equals to 5, compounded 5 times per year? Well, let's not do 5. That's kind of an unusual number. Make it, if we make it equal to 12, that makes it monthly, right? So if we let n equal to 12, then this becomes a of t equals to p1 plus r divided by 12 to the power of 12 times t. And if we let n equal to 365, compounded monthly, compounded daily, this formula becomes this way. Right, so this is compounded monthly. Compounded monthly. This one's daily. Okay. What if we wanted more than that? What if we wanted twice a day? Stop moving. Man, what's wrong with this computer? How about twice a day? I want to compound this twice a day, once at 6 a.m., once at 6 p.m. Twice a day. Well, in 1 year, it would be twice as much as this. So it'd be 365 times 2, 730 times it would get compounded in 1 year. So n would be equal to 730. And so the formula then would become a of t equals to p1 plus r over, oh man, why did this, you guys made me do it again, and you didn't say anything, I blame you. This is not 12, this is 365. So this is 730 here, raised to the power of 730 times t. Good. Okay, well, we want to keep going. What happens? What happens as n grows? Not compounded twice a day. How about compounded 3 times a day? How many times will that be in a whole year? Compounded every hour, compounded every minute, compounded every second. We want to increase the number of times we compound until we get to infinity, and we want to explore what happens there. And so that's what this little algebraic manipulation here is doing. We're taking our original formula, right? Here's our formula, and we're thinking about what happens as n goes to infinity. But before we do that, it's useful to do this kind of manipulation for it. And that's because, well, maybe an extra step would have been nice here. We have p, and we have 1 plus r over n raised to the power of nt. Okay, so here they're just introducing this result here, and you can just manipulate it because you can always multiply anything by 1. So let's multiply it by r over r, another version of 1. So that's fine. Good. And so we can separate this in the following way. We can say that this is equivalent to p times 1 plus r over n to the power of n over r n over r. Keep my r red because my n's and my r's look very similar. So that's n over r times t r. Good, and that's what this is right there. Good. Okay, so then if we think about the relationship between these two, they're kind of opposite. This is r over n, this is n over r. So they just introduced a new variable. So let the new variable m equal to n over r. N over r. Good. Therefore, if we flip it around, that must mean that 1 over m is then equal to r over n. Good. So now we can do this replacement that r over n right here, this is equal to 1 over m. One plus, right? And then n over r, that was the power of n. I hate this thing, why is it doing that? So then this is equal to n up here, m, right? N over r times tr, right? And this whole thing is kind of separated like this. Good. Okay, so now we're going to explore what happens as n goes to infinity. As n heads out to infinity, as n becomes an infinitely large number, n goes out to infinity, then n divided by a constant, r, remember r is a constant, still goes out to infinity, right? Remembering that r is some given constant value, then that still goes out to infinity. So therefore m goes out to infinity. Good? Remember r is a constant. Right? So like the n value is getting bigger and bigger and bigger. It's 1,000, it's 1,000,000, it's 10 billion, it's 7 billion, it's 7 trillion, right? It's growing. And r is just some constant number. So let's say it's just 2. If you give me a number and a half it, okay, right? It's half as big. But that number is growing out to infinity, and half of infinity is still infinity, so it's still growing out of control, right? It's still growing toward infinity. Therefore, m is growing toward infinity, since it's defined as n over r. Okay? And now this is exactly our formula for e. 1 plus 1 over m raised to the n power. As m goes to infinity, this will grow toward e. That was exactly the definition we had before, except before we had n instead of m. Same thing, m, n, it's just a dummy variable. So this process then leads you to have e. This whole thing leads to e raised to the power of tr. Good. So as n goes to infinity, this formula approaches e to the tr, or rt, and that's where this comes from, right over here. right? So we do that little manipulation there, and we get that continuously compounded interest is given by this formula, P times E to the power of RT, right? R is the interest rate per year, T is the number of years, P is the principal. Any questions? No? No? Okay, so here's an example. Find the amount after 3 years if $1,000 is invested at an interest rate of 12% per year, compounded continuously. So we saw what happened before when we invested $1,000 and compounded it every 3 months, compounded daily. So we saw what those results were before. But now if we want to compound it continuously, then the formula becomes this. A of t is equal to 1,000, the initial amount, e to the power of 3 times 0.12. Right? Another reason why e becomes so important, e helps us figure out continuously compound interest. Right? So it's key to a huge part of our financial infrastructure to use the letter e to model various equations in our economic system. 3 times 0.12 e to the power of that. And I get $1,433.33 approximately. Do you guys get the same thing? Any questions? No? No? All right, let's take another little break, and we'll get started on 4.3. All right, the next section in chapter 4. So we're out to section 4.3, which is logarithmic functions. This is a widely misunderstood section, I think. So far, I think the vast majority of everything we've done has been familiar and hopefully not too difficult. But I find in my experience that logarithms, for some reason, people don't do well with logarithms. I don't know why it is. I don't know. Maybe a lot of people skip them in previous math classes in high school. I don't know what your experience is with logarithms, but they really shouldn't be that bad. So let's begin our thinking of what logarithms are. And to do that, I want to do it through thinking about roots to begin with. So let's just take a little side detour and think about what roots are when we define them, right? I'm confident that all of us were just puzzled when we were first given that little notation. What in the world is that little house, and what does that do, right? So by default, we start off with 2, so there's like an invisible 2 there. And so we have to memorize these, right? What's the square root of 4? Okay, well, I don't know about your house, but in my house, we sat in the kitchen and my mother would hit me with a ruler every time I got it wrong. That's how you learn math. So you just had to memorize it. Square root of 4, okay, it's 2, right? Square root of 9, okay, it's 3. Right? You're just memorizing it. And the square root of 16, oh, okay, it's 4. Where does that come from? Well, it's coming from your multiplication tables, right? You have to know your multiplication tables in order to know these answers. So we know that the answer here is 2 because 2 squared is a 4, right? And we know that the answer here is 3 because 3 squared is 9, right? And we know that the answer here is 4 because 4 squared is 16. So this is really just a way of checking that you know your multiplication tables, right? It's just the multiplication tables in reverse. But if you don't know your multiplication tables, then you won't know the answer, right? So if, for example, okay, like let's get really clever here. What's the square root of 529? I don't know. I have no idea. right? There's no way to know that without technology unless you know your multiplication tables. There's nothing we can do to the 529 to get the answer, right? Just like over here, when we were trying to figure out the answer to 16, we didn't really do anything to the 16. We didn't add, divide, multiply, all those common operations we're used to. There were none of them there's no operation we can apply to this, and none of those common typical operations to get the answer. So if you don't know your multiplication table, there's just no way to know what this is, right? So you can't know the roots. You can't find the answer unless you know your multiplication tables. Now, if you happen to know your multiplication tables or you have technology, then you can find the answer. And this is, the answer is going to be 23, and that's because 23 squared is equal to 529. But you can't know that unless you know your multiplication table or you have technology. Okay, now by default, there's a little 2 that goes in here. 2 squared, 2 squared, 2 squared, 2 squared, right? And then that lets you know that we're talking about squaring all your numbers. But if we were talking about something different, what if we had the cube root? Cube root of 8. The cube root of 8 is equal to 2 again, and that's because because 2 to the third power equals to 8. But just like before, you wouldn't have known that answer unless you know your multiplication tables, unless you know that 2 times 2 times 2 equals to 8. Right? That's the only way. If you didn't know that, if I just gave this to a third grader and they don't know this is true, there's no way to find the answer for them, right? That you can't take 8 and divide it by 3. That's not going to give you the answer. You're trying to figure out blank times blank equals to 8. What is that blank? Well, that's hard to know unless you know this multiplication table, right? Okay, and then over here, if you want to find the cube root of 27, right? The answer is 3 because, again, this because 3 to the power of 3 equals to 27. Good, and so on and so forth. Okay, so cube roots and raising things to a particular power are associated. And we want to do the same sort of connection one more time. So we've been looking at exponential functions. And whenever when you do multiplication and you want to find its reverse, kind of undo the multiplication, you go to roots, right? So multiplication, 3 times 3, 4 times 4, right? Multiplication, and roots are inverse operations, right? They kind of undo each other. Okay, so now we've been working with exponential functions. So we've had something like, let's say we had f of x equals to, let's go with 2 to the x power. And we created a table of values. We've worked with this before, where we have x and we have 2 to the x power. So when we have 0, that leads us to 1. When we have 1, that leads us to 2. When we have 2, that leads us to, and we have 2, that leads us to 4. That leads us to 4. When we have 3, that leads us to 8. Right? 2 to the third power is 8. -1, that leads us to 2 to the -1 power, which is going to be 1/2. -2, that's going to be 2 to the -2 power, which leads us to 1/4, right? And so on and so forth. These are exponential functions, right? An exponential base 2. So we want to be able to go backwards, right? In reverse. What is the value of x such that 2 to the x power gives us this particular output? And that's where we defined logarithms to come in, right? So in order to go backwards, just like roots undo multiplication, logs undo exponential. So we're going to come up with this notation. Log, oh, that looks ugly. Let's erase that. Log of x, log of the input. And again, we're going to put this little base here so that people know what we're talking about. And so what happens is that we're going to be able to go backwards. Log base 2 of 8, right? This is this number right here. And so the output of that function will be this one. The answer will be 3. Log base 2 of 8 equals 3. And this is just like before because 2 to the power of 3 equals to 8. Just like when roots, right? What's the square root of 529? I have no idea. I have to know my multiplication tables to be able to get this answer. Otherwise, it's just a weird notation that I don't know how to solve. There's nothing I can do to the 529 to get the answer. I can't divide it, add it, subtract it. This little base 2 doesn't help me at all. There's just no real way of finding an answer unless you know your multiplication tables. And same thing with this. When I look at log base 2 of 8, let me copy that again, log base 2 of 8, there's no way for me to know the answer without knowing this table. I can't do anything to the 8. This 2 doesn't help me. I don't know how to fix it from here, right? I have to know this table over here. So really, this log is just something that's letting you know to go to this table and read it in reverse. And that's all you can do. There's no fancy math here. The only way I know that the answer is 3 is because I've memorized this. Just like up here. The only way I know that the square root of 16 is 4 is because I memorized it. Right? It's been memorized. And logically, it comes from knowing your multiplication tables, and I know that 4 times 4 is 16, and that's why I know it's a 4. But it's not an operational symbol. It's not an operation I can do to the 16 to give me my answer. Okay? Questions, 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 questions? So let's do a couple more then. Okay, so let's say forget the 8. Okay, how about log base 2 of 1/4? Right, what can I do, right? So this is saying 2 to what power equals to 1/4, right? So the answer to this, whatever this is, will satisfy the statement 2 to what power equals to 1/4. Right, and as I keep harping, there's no way to know that answer unless you know this table here and you understand it really well, right? People's, I don't know, maybe the word log, the fact that we have this log thing is really intimidating. You know, as you read this, people get stuck here, their eyeballs go here, and they think, log, what does carpentry have to do with math? I don't know, I don't understand that. Does this stand for something? Is this an acronym? The L stands for something, the O stands for something, the G, you know, people just get stuck with this word here, but it's just a notation, just a symbol that's asking us to read this table in reverse, right? I like to think of it as, you know, maybe ancient Greek or something, or Latin. It's ancient Latin for go to this table and read it in reverse. That's all that means. Just like the first time you saw this little root notation, you know, like, what the heck does that mean? Why are we drawing like this weird little symbol? What does that symbol mean? You know, you probably got stuck on it for a while until it became really comfortable, really familiar, and then it didn't scare you anymore. Well, this log thing seems to scare people a lot. But you shouldn't focus there. Whenever you see a log, your eyeballs should jump right into this right here. It means to read an exponential function of this base in reverse, right? So don't get stuck with this word log. Run over here and read this, right? In general, if we have a log function, log base 2 of some value x, well, let's just a and b, of some value a, then the answer is b, and that's going to be given that this means, right, because, look at the pattern, it's this raised to that power equals to this. So there's this little cycle that happens here, this raised to that power equals to this, right? So it'll be 2 to the power of b, if and only if, I should have said, not because, I should have said if and only if and only if 2 raised to the power of b equals to a. Questions so far? And of course, there's nothing special about the 2. We can also raise it to any power. So if we're thinking about a different exponential function, like f of x, say g of x is 3 to the x power. So again, we can have a table, and we can have x values, and then we can have 3 to the x power values there. 0 still leads to 1, and 1 leads to 3, and 2 leads to 9, and 3 leads to 27, right? 3 to the third power is 27, and 4 leads to 81. 4 leads to 81. Good. And negative 1 leads to 1/3, and negative 2 leads to 1/9. Good. So now if we have this, what is log base 3 of 27? This is the same thing as asking you 3 to what value equals 27? Good. That's what this is asking you. 3 to what value equals to 27? And again, the only way to know that is to know this table really well. So I'm just reading this in reverse, right? They're inverse operations. 27 is right here, therefore the answer is 3, because 3 to the third power is 27. Good. And I can say, what is log base 3 of 1/3? Oh, the answer is negative 1, because 3 to the negative 1 power equals to 1/3. Any questions, any questions, any questions? No? No? Note that, okay, so if we have log base 3 of 81, well, that's going to be 4. 3 to the fourth power equals to 81. However, log base 9 of 81 is 2, right? 9 to the second power is 81. Good. Questions, comments, issues? No. Okay, so let's get back to this thing then. Okay, so exponential functions in general, as we remember, will have this sort of a blue shape, this graph right here in blue. That general shape, as long as the base value is bigger than 1, right? Remember, bigger than 1, it has this shape. As long, if it's a value between 0 and 1, it'll flip in the other direction and come back down this way. But for values that are bigger than 1, it has this sort of a shape. It always goes through the point 0, 1, right? And notice that all exponential functions are 1-to-1, right? If we apply that horizontal line test and move around a vertical bar, that's what these red lines are. So imagine us being able to sweep this red line up and down, up and down, up and down, and keeping track of how often it crosses the blue curvature. It will always touch at exactly 1 point. It never touches at 2 points. So therefore, it's 1-to-1. Remember, 1-to-1 means that for every unique input, there's only one unique output, and that for every output, there is one unique input that led to that output. That's what it means for it to be 1-to-1. So that way we can go forwards and backwards on this. If I told you, what is the input value that led to the value B? Well, there's only one, this one. Good? Yes. Okay, so because it's 1-to-1, we know that there exists the possibility of having an inverse function. So the inverse function, f inverse, is called the logarithmic function. Right? So the logarithmic function is with base a denoted by log base a is the inverse function of the exponential function of a logarithm of an exponential function base a. Right? So that's where this is coming from. So we started working with this. We know an exponential function is this. And remember, x and y are just dummy variables. But what's important here is that they undo each other. They go forwards and backwards, right? So we started life working with exponential functions. So if we had a to the power of something in here, which is the input of an exponential function, input, usually x, but it's just a dummy variable, it doesn't matter. The input goes there, right? And then we have the base a, which is a constant, and then that led us to some output, right? Okay, but now if we want to undo this process, reverse it, get back to where we started, then that's where this logarithm situation comes from. We're going to have this new function that would denote by log base a. And now this output of the exponential, this guy, is the one that goes in there. And the output to this log function is going to be what we started with. This guy. This guy is going to be there. So it's sort of a round trip. If we started out with, just to arbitrarily pick a number, if I started out with 5 goes in there, it's going to give me some number here, some number. And we take that some number and we plug it in here. And then the output is going to be 5 again. They undo each other. Good, good, good. Questions? No. Okay, so then let's see if it helps to go back and put variables on there. And again, we use x and y way too much. So let's just pick some random number, some random letter. Let's say w is the input there. A to the w power equals to, I don't know, how about q? No, like q because of that thing. P, w, x, y, v, x, y, z. N? I don't know, how about n? Whatever. So x and y are arbitrary, we use them way too much, whatever. Let's say that in an exponential, these are exponentials over here. Exponentials. And then these are logarithms. So in exponential land, we have this. Here is our input, the w letter, right, is the inputs. And our outputs are n values. But now we come over here and we apply that value, log base a, and we apply the n in here. That becomes the new input into here. Then the output is going to be that w. Good. And that's what this is expressing. Log base a of x equals y, input gives you this output, if and only if it's true that this base raised to this power equals this. Good. So again, to this idea that there's a sort of a cycle of life that happens here. This is true if and only if this base raised to that exponent is equal to the value right in there. Right? A to the y power equals to x. Any questions so far? Good. So let a be any positive number where a is not 1. It's the only thing we're ignoring. Logarithmic function with base a denoted by log base a is defined to be this. Log base a of x equals to y if and only if it's true that a to the y power equals to x. So log base a of x is the exponent to which the base a must be raised to give x. Okay, so we can go back and forth between these two things. They give you two equivalent statements. A to the power of y equals to x is the same thing as log base a of x equals y. Okay, so let's look at some more examples. Going back and forth between logarithmic form and exponential form, so you can always go back and forth between the two. So log base 10 of 100,000 equals 5 if and only if it's true that 10 to the power of 5 equals to 10,000. Good. And we already looked at log base 2 of 8 equals 3 if and only if it's true that 2 to the third power equals to 8. Right, so whenever you see these and you want to go into from logarithmic to exponential, remember that it's this little circle here. This base to that power equals that number. Right? This base to that power equals that number. Right? That's what this is. So in general, this base to that power must be equal to that number. This is what this is. Good. It's important to understand log base a of x is an exponent. So for example, the numbers in the right-hand column of the table in the margins are the logarithms base 10. So 10 is a very popular number to use, as I mentioned a minute ago. We work with a base 10 number system, therefore some nice things happen when we work with base 10. So look at how nice this property is. If x is 1, then log base 10, right? So this guy right here, this guy is saying that if we have log base 10, and we input a 1, the answer is 0. And why is that? Well, 10 to what power equals to 1? That's what this is really asking you. 10 to what power equals to 1? And as we know, any number raised to the power of 0 must be a 1. That's why this is a 0. That's why we get an answer of 0 there. Good. And then let's say this guy right here. This is 10 squared, so log base 10 of 10 squared, right? And we know 10 squared is the same thing as 100, equals to what? Right, so that's the same thing as asking you log base 10 of 100 equals to what? Right? These both are saying the same thing. And so if we know our powers of 10, 10 to what power equals 100? Well, obviously 2. And, well, it was already given in this form, so that makes it nice and convenient. And we start to see a pattern that when the input is given in powers of the base, it matches with this base, then it's really just the exponent that equals our answer. Does that make sense? It's kind of like when we're doing square roots, square root of 9, like I don't know how to do that. But if they gave you square root of 3 squared, you're like, oh, obviously the answer is 3 because they're giving you the 9 in the form of something squared. So the square root of something squared is just going to be that number, right? So here it becomes obvious that the answer should be the 3. Well, same thing here. They're presenting you the input in terms of this base raised to an exponent. So obviously the answer is going to be that exponent. 10 to what number equals this? Remember our little cycle. This base raised to that exponent must be whatever's in there. 10 to what exponent equals to 10 squared? Well, obviously the exponent must be a 2. Right? That's why this little pattern begins to form, and things work out really nicely with base 10. So it's a very popular base to use in math, just because things work out really nicely. Some nice properties. Okay, so let's look at some of these. Again, the answer is given, but let's fill out the because. Right, our little cycle of life here. Log base 10 of 1,000 equals to 3 because 10 to the power of 3 equals 1,000. 10 to the power of 3 equals 1,000. Right? And log base 2 of 32 equals to 5 because 2 to the power of 5 equals 32. 2 to the power of 5 equals 32. Right? And the only reason I know that is because I know my powers of 2. I've had that memorized, and that's why I know that. If you don't have your powers of 2 memorized, you won't know it. Luckily for us, you don't have to have a lot of these memorized because we do have technology. So you could just type in log base 2 of 32 and just get your answer, and that's fine. but it's important to understand why the answer is 5, right? So even if you don't know your powers of 2 to a really high number, at least you can understand why the answer is what it is. Good, so then 10 to the power of negative 1, 10 to the power of negative 1 equals to 0.1. Right? That's why this is true. And finally, the answer, log base 16, log of 4 base 16, log base 16 of 4 equals to a half, if and only if it's true that 16 to the 1/2 power equals to 4, right, which is true. Good. Any questions? Okay, so that's the results we just had. When we apply the inverse function property of our functions, we get this. Log base a of a to the x equals to x, and a to the log base a of x equals to x, right? They undo each other, so they sort of represent a round trip into these functions, right? So if y equals to a of x, a to the power of x, right? We start with this input here, and we get this output. Okay, so the output is a to the x, and now we apply that whole output to log base a. Here's log base a of, and we input this y right in there, right? So we take that y and we put it right in there. Well, that y is a to the x, log base a of a to the x, because that's what y is. And then these two things will undo each other. A to what power equals to a to the x? That sounds like a simple riddle that's confusing, right? A to what power equals to a to the x? Well, this is just going to be an x. Right? That's what this is asking. A to what power equals to the thing that's in here? Well, it's definitely x. Okay, so what did we do? We started with the input of x. We applied it to the exponential function. We get an output. That output gets deposited into the log base a function, and then that undoes whatever this did and ends up giving you the same output, right? So it's kind of a round trip that happens between these two, and that's what happens with inverse functions. They undo each other. The same thing happens in reverse. If we start off by plugging something into our log function, we'll get some output. We plug that into the exponential function, and they undo each other. And so we undo those two functions, undo each other, and we get back to the number we started with. For that reason, there's some nice properties of logs we have to remember. Right? Remember, a log is a function. It's a set of instructions. It's telling you to go look at a table and read it in reverse. It's not a traditional mathematical operation like adding, subtracting, dividing. So therefore, we have to be very careful about what operations we apply, what rules apply to logs. And so they're going to be very clearly outlined, the rules that apply to logs. And only these rules apply to logs. Well, you should only stick to these rules because it's not true that you can just do whatever you want. Distribution doesn't work the same way, and division doesn't work the same way, right? There's a lot of things we can't do. So we have to be careful about what we are allowed to do. And here are a list of some of those properties that are true. Log base a of 1 equals 0, and that's true no matter what, because remember that this little cycle occurs here. This is saying that a to the power of 0 equals to 1, and that's true no matter what a is, as long as we're looking at a as being a positive number, right? So for all of these, a is strictly greater than 0. A is strictly greater than 0, and a does not equal 1. That's what the value of a is, just like any other exponential number. Okay, so any number raised to the power of 0 is 1. Also, a to the power of 1 equals a. That makes sense. So log base a of a equals 1 is another true statement. A to the power of x equals a to the power of x. So that's another true statement. Good. And then this last one, like I said, is a little bit more confusing. It comes from this property right here, which is why it's, you know, it's not as pretty. But let's just try and use one little example to see what it's saying, and we'll see that these two operations undo each other when we get to that. So let's say, for example, we have that log base 3 of 81 equals to 4, right? That's because 3 to the 4th power equals 81. Okay? Because 3 to the 4th power equals 81. So this is a 4. You can say this in place of a 4, right? When my nephew turned 4 years old, I put this on his birthday cake, right? You're turning log base 3 of 81. Congratulations. Blow out your candles. Right? It's the same thing. When you learn to count, you can count 1, 2, 3, log base 3 of 81, 5, 6, 7, right? This is 4. Okay, so you could say 4 times 3 equals to 12, or you could say log base 3 of 81 times 3 equals to 12, right? It's a replacement of it. It equals to 4. Just like square root of 16, you could say 1, 2, 3, square root of 16, 5, 6, 7, 8, right? It's a 4. Okay, so given that it's definitely absolutely a 4, then you could say that 3 to the power of 4 is the same thing as 3 to the power of log base 3 of 81. Right? Because this is 4. We just established log base 3 of 81 is a 4. Okay, well, over here, I clearly know this is 81 by knowing my powers of 3. 3 times 3 times 3 times 3. Whereas here, well, someone that doesn't really know their powers of 3 can notice the pattern that we have an exponential number, base 3, and we have a log being raised to an exponent that is also a log, base 3. So these two match, and we have an input of 81. The whole thing just equals to 81. Right? Since this is a 4. Good. Think of it this way. The reason it's an 81, right? So log base 3 of 81 equals to 4 because, thinking of our little circle here, because 3 to this power equals to 81. So even if you didn't know the actual number, it would still match. So if I had, the pattern would continue. So if I had something like 7 raised to the power of log base 7 of some ugly number, I don't know, 537, something like that. Okay, so I can kind of think about this on the side. What is log base 7 of 537? I don't know. It's equal to some number. Let's leave it as a variable. About, I don't know, it equals to m. And it equals to lowercase q. What does that mean? It means that there is some decimal number out there such that 7 to that decimal number equals to, such that 7 to the decimal number q equals to 537, right? Q is that number. There's some real number out there so that 7 to the power of that decimal equals to 537, right? So this whole thing is that decimal. The decimal such that 5 to the power of 7 to the power of this decimal, right? This equals some decimal q, right? And q is the number such that 7 to the power of q equals to that. So now what do you get when you take 7 to that power? Well, it's kind of like, no duh, it's exactly the 537. It's a riddle, right? It's like a really obvious riddle that is so obvious that it gets a little confusing, right? This is, by definition, a decimal value, some number, some real number, such that 7 to the power of that decimal equals to 537, right? So get that decimal in your head. And now what do you get when you get 7 raised to that decimal? Well, it's 537. You just told me that this is the decimal that makes this true. Okay, so these two things, as long as they match, this exponent, this base, and this little number, this little index to the log, as long as they match, the output is going to be whatever number is in there. Any questions about that? No? 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 I think that's probably the most complicated sort of property that's presented. And so here's some examples of our properties. Log base 5 of 1 equals to 0, and that's why? Because 5 to the 0 power equals to 1. Property number 1, 5 to the 0 power equals to 1. That's why. And log base 5 of 5 to the 8th power, right? Like I can go ahead and figure out what this is. 5 to the 8th power, some huge number. And 5 to the 8th power equals to 5 to the 8th power. So this is kind of an obvious thing. This to this power must be this. So when it's given an exponential form and these two match, well, then the answer is just whatever's in there. Good. And then over here, of course, this one's an easy one. 5 to the 1 power equals to 5. Good. And then this is the one I just mentioned. Log base 5 of 12 in the exponent, 5 to what power? Well, then, of course, we get the same thing. So, for example, let me jump to the answer here. Let me do this. Divided by... using my calculator, we'll get to this in a second, but using my calculator, I know that log base 5 of 12 equals to 1.543959 dot, 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 dot. Why is that the answer? Because it must be true that 5 raised to this exponent, 1.543959, must be equal to 12. Right? And we can check it with our calculator. 5 raised to the power of 1.543959, rounding, of course. From my calculator, I get approximately 11.999. You can check it. It gives you approximately equal to 12. So log base 5 of 12 is this decimal, right? They equal each other. So when they ask you this question, what is 5 to the power of log base 5 of 12? They're really asking you this. You can also say, what is 5 to the power of 1.543959? Okay, it looks extra confusing here. Like, how are you supposed to know 5 raised to the power of 1.549? What is that equal to? You know, it's kind of hard when you're staring at this. But when you're staring at it in this form, it should make sense, since the answer to this is the decimal such that 5 to the power of that decimal equals to 12. So that's why this answer has to be 12. Any questions about that? No? 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 Okay, this is a good place to stop then. So you can begin some of these questions about finding logs, and we'll continue tomorrow with the graphs of logs, and we'll pick up from there tomorrow. Okay, cool. Any questions at all about anything?